Just a small correction for this video, that the page of workbook of these pictures is page 51. Sorry for this. Okay, let's have a quick look on cascaded loops. That is the last structure plan signal block diagram on page 51. Note what now has happened with our original loop. This is our original process, actuator, sensor, process. Here our original Z2, which makes problem. This is our, that is a new PI controller. You see here we have not a PID but a PI. Here we have a PID, a second PID. So not added just in series connection, but with an internal new feedback. That is new. So we have here an internal loop and an external loop. So now we have a two loop system, and that is called cascaded loop. The cascading principle. Now an internal loop, and this is influenced by the output of the outside controller, influenced by the controlled output X. Note that this changed our original PID design. You can throw it away. If you go to cascaded loops, then forget all about single loop design, what you have done. In our previous improvement methods, the original PID is not changed, because this change has nothing to do with the dynamic of the loop. This change also has nothing to do with the dynamic of the loop. Just an addition, but not a dynamical change, so the PID is unchanged. But now the dynamical situation is changed because we have added in the original loop a new block, a new second controller, and an internal feedback. So you have to redesign your controller, and much more. In the cascaded loop you have to design two controllers, and that is not the only additional step. We will see just in a few minutes that the design of a cascaded loop system is much more time consuming, but the effect is rather good. Okay, this sign is new. That has nothing to do here in my picture. Oh, I have just see this sign. Forget this sign. Okay, the principle is very simple. What do you need more? You need here a junction point. That means you have to measure an internal physical variable. You need not a disturbance sensor, you need a sensor for an internal value. So you have to change the hardware of your system, or have to find a position where you can measure internal values. For example, very typical application is in a motor-driven system, that you measure the current, the internal current of the motor, the anchor. So you need here an internal current sensor of, if this is an AC current, an AC sensor for currents. That could be not so easy to add this, but this is a condition for a closed loop system with cascaded loop, that you have an internal sensor for internal variables. If the sensor gives a value, then you can add as internal feedback, negative feedback. And what happens is now that if Z2 is changed, automatically at once XE is changed, and this change then is sent to my internal controller. The reaction can come at once with the differentiator very quickly at once, and the reaction has to go through FS1 and FS2 and then can compensate Z2. So the way to compensate Z2 is much shorter. The way is as short as in this example, but this previous example, but here you have a different principle, which has additional advantages. Okay, with this internal feedback, you see this loop behaves like a closed loop system, And this controller now sees, the error is missing, sees the process for this outside external controller is closed loop internal system plus FS3 plus FS4. So this controller not directly see FS1, FS2, but the closed loop internal system. So the design goes now in 3 steps. I will note these 3 steps in more detail. The first step is you have to design the internal PID. Where the FS1 and FS2 blocks are the process. This internal closed loop system is not influenced by FS3, FS4 and this PI controller, so you just look for this internal system. So I make now a block around this internal system up exactly to this point, and this is called FW internal. That is a closed loop internal system. So after design we need information of the behavior of this closed loop internal system, because for the design of the PI controller we need the dynamics of this internal closed system, and we have to add then these both blocks, and then we can design the second controller. So advantages. As I have mentioned, first, the way to compensate Z2 is shorter than a single loop system. Yeah, way is shorter for compensation of Z2, because the way of the reaction, the compensation, has only to go through FS1 and FS2. That's the first thing, so we can have much faster compensation of Z2. Second, the internal PID has only 2 parts of the processes instead of 4, works only on FS1, FS2. What does that mean? The gain of this controller can be much larger than before, where the PID works on 4 loops, because the negative phases of these blocks has no influence to the phase margin of the internal controller. So the gain can be much larger and the closed loop behavior much faster than before. So the negative phases of FS3 and FS4 have no influence. Ki could be much larger. And if the gain is much larger, the system is fast. Internal system is much faster than before. So that is a main advantage. And furthermore, if there are non-linearities, you have to know if gain is very large, also non-linearities have not so big influence. We have better behavior also in non-linearity situations. And third advantage is following. If this controller is well designed, that is a condition. then we assume that this value and this value, after change, very quickly have the same value. So with wi, you control xi. That is the task of this controller, with the advantage that you have a control about this internal value. Assume this is the anchor current. We can avoid a too high current by just limiting the desired value here. Yeah? To limit, for example, limit xi, or do any other thing. Assume a limiter for this current in an ICE motor. Maybe this is current in the range of 1000 amperes AC. Imagine that a limiter of this current is really not possible or affordable, just 1 cubic meter semiconductors. Here with this loop you need just a sensor for this signal, and then the limitation is done with the desired value of the internal loop. So with this value you have very good control over that value, and this is very often a help to avoid damage caused by too high currents. Yeah, with limiting wi. Yeah, that is a very big advantage in high power systems. Okay, now let's have a quick look for the design steps. Instead of the one PID design in the original situation, here you need a Bode plot or signal block diagram of these 4 blocks, design the PID controller, and that's all. Now you have to design this PID, and before you can design the external PI controller, you need the dynamical behavior of the internal closed loop. So there is a 3-step design. Design internal PID, calculate closed loop internal behavior, then design out external PI. So 3 steps. First, design internal controller. We have learned several different design methods. In our lecture we have seen 3 methods. Simple design, like project 1. PI with 1 PT1 or I with 1 PT1 or P with 1 PT1. Yeah, that is often possible, that or a PI with I process or PI with IT1. No, not that is project 2. Sorry, that is too fast. Yeah, if you have a simple design with these combinations, look into project number 1, cruise control. If in case B, the internal loop with FS1 and FS2 behaves like the combination we have found in the what I have called flash control design. Use flash control. Workbook page 33 gives some examples. The combination of PID T1 with 2 PT1s or PDT1 with IT1. This is possible. Yeah, if this combination appears here in your internal loop, use flash control. If A not possible and B not possible, in C, of course, you can make an FRA design. Using Bode plot of fs1 plus fs2. So just depends on your application which case you have to do here, and this influences the next step. Calculate closed internal loop dynamics. I have called FWI for internal. In case A, with simple transfer system calculation. We will do an example in the next step, or you have to look into project 1 to look what I mentioned, what I mean with this. In B, if you can apply flash control, FWE is always a PT2 block. Now that is the result of the design of my flash control. If I do this, including pole compensation, of course, then we know the closed loop behavior is exactly a PT2 behavior. So we know that the red section here behaves like a PT2. In C, if the only way to design a controller is using FRA design, and you have only the Bode plots of the open loop, then you have to calculate Bode plot of closed loop of FWE using Nichols equations. C page workbook 34. I have to check it. Yes, page 34 is correct. So you know the open loop Bode plot. You have to add Bode plot internal F controller I to your process fs1 plus fs2, and then calculate some points, of FWE. In magnitude and in phase. Yeah, that is a very time-consuming thing. So for examinations, point C here is not very useful, because this takes sometimes hours, because this is a conversion point to point of a Bode plot into a new Bode plot, and with the calculator you take for each point some minutes, and if you want to have 10 points, then you have quickly 30 minutes to do. So this is possible. There is a way to do this, but in our examples mostly we can apply example step 2a or 2b. If step 2 is done, then go to design the external controller, design external FCE with appropriate method, because this depends on step A, B, C and FS FC external plus FS3 plus FS4 is now the process for design. Yeah, depends on what is FS3, FS4. What is this? Is this just a simple PT1, or here is this a simple PT2? Or in C, this is the Bode plot, and if you know the Bode plot of the closed loop system, you have to add the Bode plots of FS3 and FS4, and this is also a time-consuming way, and then do the design for the like FRA design using the Bode plots. So this is the end of the theory of this lecture, Control System 1, and of lecture Control System 1. What I want to add now for the next videos, I want to add some exercises. The first exercise is just an application of cascaded control design with I think nearly all methods, but of course this should be a new video. This is then video number 64.